Hello, I am Dr. Ajay Sharma, Department of Electronics and Communication Engineering, James Engineering Management Technical Campus, Knowledge Park 3rd, Greater Noida. The subject that I teach in this semester for BTech final year students is Optoelectronics and Optical Communication. This subject is main subject for the final year students, and the topic that I discussed in this video lecture is about optical sources. In that, we discuss about design LED, which is an optical source for optical communication. Optical source is main part of optical transmitter, and the duty that optical transmitter assigned to this optical source is very important, because optical source convert electrical signal into a optical signal, right? So we need a conversion, because we know that the signal that is flow through the or propagate through the optical fiber is the light. So the information is converted into a light. So the information that you have, which is in the form of electrical signal, should be converted into its equivalent light signal, and that particular task is performed by the optical source. So optical source is there is some connectivity issue uh, because the internet quality is poor. That's why there is a disconnection. Okay, come to again this optical source. So the function of this optical source is to convert an electrical signal to an optical signal, permitting the transfer of data along an optical fiber. So that the optical source convert this electrical signal, of course, this is the information signal, into optical signal, which is a light signal, and that light signal have some data. So this is we call as a data signal, right? Data signal in the form of light signal, and that signal is propagated through optical fiber. So if you look at the picture, we have input data. If nowadays we have communication is digital based, so sometimes we have a data which is in the form of 10 format. So that 10 format, of course, that have come in the category of electrical signal, is converted into a light signal. So we have a we need to now what, so once the light is converted, once this electrical signal is converted into optical signal, then we need a modulation also, So the modulation technique that we used in optical communication is on-off technique. So we have a pulses of on and off pulses. On means on represent 1 and off represent 0. So these are the optical pulses. So presence of light means 1 and absence of light means 0. So that types of pulses to be transmitted through optical fiber, right? So basically the fiber optic device is responsible for that signal conversion is a fiber optic transmitter. So transmitter is basically a main part of optical communication that has the responsibility to convert electrical signal into a light signal. Now, so a fiber optic transmitter converts electrical signals into optical signals and launches optical signal into an optical fiber. So once you have a light at the output of the light source, now that light source should be launched into the optical fiber. That is act as a guide or wave guide for the light to propagate through it. So fiber optic transmitter consists of basically 3 parts: interface circuit, a source drive circuit, and an optical source. So the interface circuit accepts the incoming electrical signal and processes to make it compatible with the source driver circuit, right? So what's the function of this interface circuit is to accept the electrical input, because the input is always an electrical signal. So accept that signal and process it to make with compatible with the source driver circuit, and this source driver circuit derive LED or laser, because LED and laser both are the light sources, optical sources that we use in optical communication. So the source driver circuit intensity modulates the optical source by varying the current through the source. So with the variation in the current, there is a equivalent variation in the intensity of the light, right? So we can say that the light is modulated because there is a change in the intensity according to the change in the electrical signal. So an optical source converts electrical energy into optical energy, means current into light. So the light emitted by an optical source is launched or coupled into an optical fiber for transmission. So once you have a light from the optical source, this light should be launched or coupled into an optical fiber for smooth transmission in optical communication. So fiber optic data link performance actually depends upon the amount of light or power launched into the optical fiber. This is one of the issues. So once you have a light at the output of the transmitter, that light is 100% be launched into the optical fiber. Sometimes because of leakage and because of improper placement of optical source and fiber, there is a leakage of optical energy. So that degrades the performance of optical communication. So what we need 100% of the light is launched into the optical fiber. So whatever the light that is coming from optical source is totally goes into the optical fibers, nothing to be reached outside. So the development of efficient semiconductor optical sources along with the low loss optical fibers led to substantial improvement in fiber optic communication. So nowadays we developed very in optical communication, as far as improvement in the communication is concerned, we have to improve our optical communication by using very efficient semiconductor optical sources and use very low loss optical fibers. So by using best optical source and best optical fiber in the sense of low loss, then we can improve the optical communication system. So what we need actually from optical sources and what we desire actually. Number one, be compatible in size to low loss optical fiber, means the size of the optical source should be compatible with the size of low loss optical fiber by having a small light emitting areas capable of launching light into a fiber. So number one, be compatible in size in low loss optical fibers by having a small light emitting area capable of launching light into fiber. Second, launching sufficient optical power into the optical fiber. That is a very essential need that we have. We have to launch 100% of the power into optical fiber to overcome fiber attenuation and connection losses, allowing the fiber signal detection at the receiver. Third, emit light at wavelength that minimize optical fiber loss and dispersion. So we use that type of wavelength that minimize optical fiber loss and dispersion. And the fourth one, optical sources should have a narrow spectral width to minimize dispersion. So we need a fine light. We need a fine light, and that fine light means narrow spectral width, and that minimize a dispersion, which is act as a loss. allow the direct modulation of optical output power. So direct modulation is needed as far as optical output is concerned. So we have to maintain a stable operation in changing environment condition, because conditions of the atmospheric condition, you can't do anything with that because that change with time. So we have to maintain a stable operation in changing environment conditions such as temperature, and cost less and more reliable than electrical devices, permitting fiber optic communication system to compete with conventional systems, right? So we have to make optical communication is friendly with the environment conditions that change with respect to time. So we need more reliable electrical devices that are used in high temperature and low temperature also. So semiconductor optical sources suitable for fiber optic system range from inexpensive light emitting diodes to more expensive semiconductor lasers. So we have various types of LEDs and lasers are available in the market and have different costs depending on the quality of light that you want. Of course, laser has better quality of light that you have rather than LEDs. And but nowadays LED is also advanced. We have a super luminance LEDs. So we use that So semiconductor LEDs and laser diodes are the principal light sources used in optical fibers. So basically, two optical sources are available in optical communication to use. One is LED, another is LD, light emitting diodes and laser diodes. As far as the operating wavelength is concerned, we have to choose operating wavelength that have minimum losses. So fiber optic communication system operates in 850 nanometer, 1300 nanometer, and 1550 nanometer. These are the three windows that are available. So optical engineer use one of them, rather they choose around 850 or 1300 or 1550, depending upon the environment and what type of optical communication that the engineers want to establish. So semiconductor sources are designed to operate at wavelength that minimize optical fiber absorption and maximum system bandwidth. So we have to choose that type of wavelength that do two things. One, to minimize losses that are come in the form of absorption, and second, we maximize the bandwidth, means the capacity that we want is more. We want more information is to be transferred with optical fiber. So by designing an optical source to operate at specific wavelengths, like absorption for impurities in the optical fiber such as hydroxyl, OH ions can be minimized. As you know, OH ion is come into the optical fiber during the process of manufacturing of this fiber, because there is impact of water on this molten state of optical fiber to cool down. For that, OH ions are found in optical fiber, and these OH ions are responsible for the optical absorption, right? So we use that specific wavelength that have no effect of this OH ions, or you may say absorption. And OH ion is one of the impurities of optical fiber. So maximum system bandwidth involves designing optical fibers and sources that minimize chromatic and intermodal dispersion at the intended operating wavelength. So we choose that type of wavelength that have minimum chromatic and intermodal dispersion. These are the losses that are coming in the picture, and both the terms we already familiar with that, and in my previous video lectures we already focused on these chromatic and intermodal dispersions. So students are also aware of that. So we choose that type of wavelength in optical communication that minimize the optical losses, maximize the bandwidth, maximize the capacity, and minimize the intermodal or chromatic dispersions. So initially, the material properties of semiconductor optical sources provided for optical emission is the 850 nanometer wavelength region. So nowadays, most of the optical communication engineer use 850 nanometer wavelength region, because an 850 nanometer of operational wavelength avoids fiber absorption loss from OH impurities near the 900 nanometer wavelength. So this is the reason why we choose 850 nanometer to avoid this absorption loss. So the light sources from 850 nanometer system were originally semiconductor LEDs and laser. So this 850 nanometer wavelength is wavelength of light that is coming from either LED or laser. So both the optical sources are capable to give you 850 nanometer light. So currently in the most 850 nanometer systems uses LEDs as a light source. For actually normally 90% 850 nanometer wavelength. If you want 850 nanometer wavelength light, that most probably you use light emitting diodes, or you may say LEDs. So this is all about this optical sources or LEDs, and these are the optical sources. So this particular unit is start with that. So we will focus on LED and laser, the working of LED and laser later in video lectures. So for meanwhile, that's all. Thank you very much.